but it's not showing.
Do you also need to start recording?
Yeah. All right. All right. So I think it's just audio.
Okay. Thank you. All right. Reconnecting this. Hopefully this will connect. Awesome. Hey Joseph. This is no longer working. Okay, cool. Thank you.
Yeah.
Okay. All right, so we just talked about the 68, 95, 99.7 rule. To recap, we know from above that a normal distribution, bless you, for IQ follows a normal distribution with a mean of 100 and a population standard deviation of 15. So I'd like 3 volunteers to walk through this. So for the first, what percentage of individuals have an IQ between 85 and 115? Maybe someone we haven't heard from yet. John.
68.
Okay, 68. How did you get that?
Well, following the 68% rule. So that's 85 is 1 centimeter below, and then 1 centimeter above the mean. So it's within that 68%.
Okay, good. Remember that we can show that for a normal distribution, 68% of observations will fall within plus or minus 1 standard deviation, or 1 population standard deviation of the population mean. Since we know that the population mean is 100, we know that if we went down to 85 and up to 115, 60% of observations should fall between 85 and 115. So next, what percentage of individuals have an IQ of above 100? Mike? 50? How did you get that?
Because they put the median at 100.
But that's not part of the 60, 80, 95, 99.7. No, that's okay. It doesn't matter. So yeah, in this case, what percentage of individuals have an IQ above 100? As Adi mentioned earlier, and as we have in the notes, we know that the mean is equal to the median is equal to the mode if something is exactly normally distributed. So what percentage of individuals have an IQ above 100? Since we know 100 is the mean, 100 must also be the median, and by definition of the median, we know that 50% of people have an IQ of above 100. And then the last thing is, what percentage of individuals have an IQ between 85 and 130? Swarm.
So what we did, we first, because it's in the range of 85 to plus 2 standard deviations past the mu, we first just took 68%, then we wanted to find what that chunk was between the first and second standard deviation. So we took the difference from 95 and 68, that was 27%, divided it by 2, we got 13.5, and we simply added that on to 68%, so we got 81.5.
Okay, good. So to recap, they recognize that, by looking at the normal distribution, you can think of it as a geometry problem. We've already got this piece here shaded in, which is plus or minus 1 standard deviation. We already know that that is 68% of all observations in between 85 and 115. That was also our answer to question 1, which John answered. Then your goal is to find how many people fall in between 115 and 130. So they said, we know that 95% of people fall in between 70 and 130. We know that this chunk is 68%. The 85 to 115 is 68%. So what's left over here in the 70 to 85 or the 115 to 130 is 27%. Taking half of that, they know that this piece between 115 and 130 must be 13.5%. 68 plus 13.5 gives you 81.5%. So that is, so good. That is the answer to what percentage of individuals have an IQ between 85 and 130. And this, I just noticed this isn't super clear. So I do that a lot. I just do like a dot. So if it's ever unclear, let me know. Perfect. Does anybody have any questions about this stuff? All right. So moving on. This is really, really phenomenal to have, but let's go into something else. Like, while it's nice to have the 60, 95, 99.7 rule, let's generalize this to be able to calculate the z-score of a particular observation. So I have a formula here that tells us how to calculate the z-score. I'm also going to write it on the board so that it is typeset in a more palatable manner. So to calculate the z-score for observation I, we've got zi is equal to xi minus the population mean divided by the standard deviation. And these should be the population mean and the standard deviation of x. Sometimes you'll notice that we have mu of x and standard deviation of x. What this is doing is this allows us to measure for each observation xi, it allows us to measure how far each of these observations is away from the population mean in terms of standard deviation. So if we were to say, let's look at a quick example. Let's say that someone has an IQ of 115. We want to calculate the z-score for that person. So we take 115 minus the population mean, or the mean of IQ, which is 100. We divide that by the standard deviation of x, or the standard deviation of IQ, which is 15. Obviously, it gets us 15 over 15, which is 1. So this particular observation has a z-score of 1. Makes sense. We know this person is 1 standard deviation above the mean. If I were to replace this 115 with 130, we would get a z-score of 2 because it's exactly 2 standard deviations above the mean. Now, the 68, 95, 99.7 rule was nice because it told us how many people would fall within 1 or 2 or 3 standard deviations exactly. But this allows us to get at people who might not fall exactly 1 or 2 or 3 standard deviations above or below the mean. we know that. So, does anybody have any questions with that?
So it
Yeah.
it gives you for each value how far it is by terms of standard deviation.
Correct. So, what you can do is you can calculate a z-score for every observation in your data set, if that is something that you want to do. So, you take each observation individually minus the mean divided by the standard deviation. And it will tell you how many standard deviations above or below the mean that particular observation is. Remember that if we wanted to look at how x is distributed, I'll get rid of this here. We know that x is distributed, or IQ is distributed, according to a normal distribution with mean mu and standard deviation sigma. We could get specific, but let's just keep it x instead of looking at IQ 115. So x follows a normal distribution with mean mu and standard deviation sigma. Z, if we take every value in the population of x, so x is IQ, x is whatever, and if we take every observation using this formula here and replace the x observation with its corresponding z-score for the whole population, we will find that z follows a normal distribution with mean 0 and standard deviation 1. This is going to be really beneficial to have. So if you've taken stats classes before, you were probably given maybe during exams a list of tables, that you would be able to look at during your exam. And what you're doing is you would be looking at particular values on the z distribution, or the standard normal distribution. We call this, the standard normal. And it tells you if you have a z-score of this, it tells you exactly how many or what proportion of observations would be above that or below that. So this is nice because we can take any normally distributed value x and turn it into z, the standard normal. All you have to do is for every single observation, take away the mean, divide by the standard deviation. Now, when you would get those tables for your tests and stuff, you might have only had a couple of sheets of paper because they assumed, hey, the standard normal is going to have a mean of 0 and a standard deviation of 1. If you tried to have a different table for every possible value of mu and every possible value of sigma, you wouldn't be able to do that. There's not enough paper in the universe to be able to do that. So that's why it's helpful for us, not just on tests, but it's also helpful for other reasons, to standardize x in terms of z-scores. So if you want to pull up a Jupyter Notebook or Spider or Python in your terminal, what we'll do is, let's see. Let me pull it up on our screen here. I want to get it off full screen. All right. So here we go. I've got Python on my screen here. And what we want to do is we want to type in import numpy as np, and I'm going to put in this array of values, 3, 4, 5. Remember, you're going to have to put it in a list. So import numpy as np, values equals np.array, list of 3, 4, 5, hit enter. If you get some error, it's possible that you didn't put this into a list. Your array should only take in one argument. Now we want to do from SciPy import stats, and then stats.c score values. From SciPy import stats, and then stats.z score of values. Oops. What you should get is something that looks like this. You should get an array, negative 1.22, 0, and positive 1.22. All right? So negative 1.22, what is that telling us? All right, so I guess we have to leave the building. Yeah.
On the screen.
Okay.